Okay, let's start. So, good morning, everyone. I'm Nathalie Grisey. I work for RTE, the French Transmission System Operator, and I have the great pleasure to be the OSMOSE coordinator and to be also the moderator of today's webinar. So, welcome to this webinar, which is organized by the two H2020 project, OSMOSE and EU-SysFlex. For your information, yesterday we had the previous webinar related to the question of high-risk scenarios and related challenges and solutions proposed by our project. And tomorrow we'll have another webinar on the topic of distributed flexibilities. If you could not attend this webinar and if you cannot attend this one entirely, please note that they are recorded and they will be available on our website and YouTube channels of our two projects. Today, the topic is IT challenges to activate and monitor flexibilities. Indeed, digitalization is a key enabler in our evolving power system. We are developing a lot of new solutions to decarbonize our power system, and most of them are relying somehow on digitalizations, and we are facing new challenges, and of course, we're developing solutions to address those challenges, I think. Next slide, Christina, please. So first today we'll have an introduction of our two projects, OSMOSE and EU-SysFlex. And from OSMOSE we'll have three presentations from two of our demonstrators, where we'll give you some flavors of the challenges we encountered when going to real operations and how we could solve them. From EU-SysFlex we'll have also two presentations on a generic platform they have developed to exchange data, energy data, and we'll see what are the benefits of such a platform in future flexibility projects. And finally, we'll have also a presentation from OSMOSE on the IEC 61850 standard and what could be the benefits in such projects. Thank you, Christina. Next slide. A few practical details for this webinar. Can you use the Q&A section of Zoom to ask your question? Please mention the speaker to whom you address your question, or at least the slide number or the presentation, so that we can easily know to whom the question is addressed. We'll try to take one or two questions after each presentation if we have the time. Otherwise, we'll try to keep a Q&A session at the end. And still, if we cannot address all the questions, we will try to answer by email after the webinar. All right, so I will start with introduction to the OSMOSE project. Next slide, please. Thank you. So OSMOSE is a project about flexibility. There are many possible definitions of what is flexibility. Our in the project is the following. It's the power system's ability to cope with variability and uncertainty in demand, generation, and grid over different timescales. It means we consider that flexibility is not only a short-term issue, because actually there can be some relations between the short-term and the long-term issues. And thus in our evolving power system, we see, of course, new needs of flexibility arising related to the penetration of renewables, but also to the electrification of demand. But fortunately, we also see new sources of flexibility, like storage, but also the flexibility of demand, of renewable generation, and even of the grid. And thus in our project, we try to see how we can address the new needs with the new sources in the most effective way. Our consortium, so we are H2020 project funded by the European Commission with 27 million euros budget, 33 partners from 9 countries, as you can see on the picture, with TSOs, with industrials, with academics partners. With the work package leaders of our project, so it's RTE, Electrica, Terna, ELES, CEA, and Berlin. We started in January 2018, and the project will end in April 2022, so next year. We are entering our final year, basically. Next slide. So the content of our project. So first, we have 2 work packages dealing with simulations of long-term scenarios. Here, our target is to identify future needs and sources of flexibility and develop new tools and methods for flexibility assessment. On the other end of the project, on the right part of the slide, we have 4 large-scale demonstrators where we want to foster the participation of new flexibility providers and also demonstrate new flexibility services and assess multi-services capabilities. Those four demonstrators are led by transmission system operators. And in between, so we have one work packages, which is dealing with scaling up and replication activities. Next slide, please. So in today's webinar, sure we'll not address everything what we're doing in the project, but we'll have presentation from 3 of our work packages. First one will be from our work package 6, which is near real-time cross-border energy market. Then we'll have presentations from our work package 3, which is grid farming by multi-services hybrid storage. And our final presentation from OSMOSE will be from our work package scaling up and replication. That's all from me, and enjoy this webinar. And so, Marianne, the floor is yours. I cannot hear you, Marianne. I don't know if it's my...
It's me. Sorry, can you hear me now?
Yes.
Yeah, the right microphone is a good option. So good morning, everyone, and thank you very much, Nathalie, for the introduction. I'm very pleased to introduce you to the EU-SysFlex projects. I'm Marianne Evans from EDF R&D, and I'm the technical manager of the EU-SysFlex projects. So first slides gives you the facts and figures of the EU-SysFlex project. Similar as OSMOSE, as Nathalie was saying, it's answering a call on low carbon energy and the flexibilities to be introduced and developed in the future power system with 50% renewable energy. As you can see, it's a large consortium, large project with 34 organizations from TSOs to DSO aggregators, technology providers, and of course, research institutes and universities. It has a budget of 26.5 million, which 20 million are funded by the H2020 program. It will last until February 2022, so for 4 years. It's a big project and has 12 work packages. 2 of them will be introduced today because they focus on data management and data exchanges and the challenges with it. One which is more dedicated to developing models, and that will be presented by Kalle Cook from Ellering, and one which is focused on demonstrating solutions and especially flexibility platforms, and that will be presented by our colleague from ACA. Next slide, please. So the context and the concept of the EU-SysFlex projects. We study the overall increase in system complexity when we progress towards more renewable energy. Part of it, so from 30% to up to 50% and more. For those who attended the webinar yesterday, you saw that we had several scenarios with over 50% res. In all these scenarios, what we could see is that there will be a greater reliance on the variable generation, in particular wind and solar. There will be some changes as well in the demand side, especially in terms of new electric uses, such as electric heating and electric vehicles and transport mobility. And this will also lead, because these new sources are very decentralized, so this will lead to changes in the system structure as well, as it is becoming more decentralized and more distributed, connected to the lower voltage of the power system. So yeah, and in parallel, of course, the electricity use is estimated to increase with the new uses from 20% to 40% of the energy needs with smarter living as well. So this leads to some challenges. As I was saying, what we will focus on today is the fact that these sources are variable, but also decentralized. Sources of electricity, but also we have studied and demonstrated some flexibility solutions in the various work packages of the project. And what we can see is that, as Nathalie was mentioning for OSMOSE as well, some of the flexibility solutions come from decentralized sources as well, from prosumers, from demand side response. So we're progressing here. You can see the core scenarios of the EU-SysFlex, from energy transition to renewable ambition, with an increasing share, so not only of RES in the power system, but part of it, as you can see below in the figures, more than half of it in the renewable ambition scenario is variable and decentralized generation, with different levels of development depending on the countries, and so different impacts depending on the countries. So, as I was saying, the sources of electricity, just if you can come back on the key message, the sources of electricity, but also of needed flexibility, are increasingly decentralized. They're also much smaller compared with conventional flexibility provided by power plants, and they're numerous as well. So they need to be accessed, they need to be interfaced, and they need to be coordinated between the different energy system players, and including the new players. Next slide, please. And this leads us to my last slide to introduce today's webinar. Is a key enabler to be able to succeed in this new power system, is the interoperability and the exchange of energy and flexibility data in a secure and reliable way. So as I was saying, flexibility solutions that we have studied in the various simulations and demonstrations come from smaller, numerous decentralized sources. We've studied flexibilities provided by variable RES themselves, by decentralized storage, by electric vehicles, by demand-side response. And so this led to the study of various system use cases in order to access in a secure and reliable way the data, to manage them, to authenticate them, to verify the performances, which was a key point in the project, especially in the demonstration. So the digitalization challenge relies also on interoperability, the fact that we're capable of interfacing various systems, work on especially formatting of the data and standards to be used in order to interface the systems in a correct way, and exchanges between players. So especially because we have some real-time data exchanges, and how they can be supported, especially by data exchange platforms and flexibility platforms, as I was saying in the introduction, our colleague Mandibi will present that as well. So have a great webinar, and I hope you enjoy the presentations.
Thank you very much, Marianne. So now we'll give the floor to Gregor Goricar from ELES. So Gregor, if you want to take the control. Yes, you have moved the slides. We cannot hear you so far. Gregor, can you hear us?
Okay, I can hear you.
Okay, great.
I had some difficulties with this while you give me the
okay, you can go back. The slides are before.
Just a second. I hope I will find it now.
No, it's before. It's before, Gregor.
Just a second.
Great.
Okay. Thank you. Hello to everyone, and sorry for this early starter. I would like to first introduce the OSMOSE work package 6 in a few words to all of you. So the objective of OSMOSE work package 6 is to experiment close to real-time joint optimization of generation, storage, demand, and grid in a closed loop in order to extract the most value from remaining flexibilities of the electrical system. The target mechanism and the concept enabling this optimization, named Flex Energy Market, is proposal of new voluntary market aiming at performing a physical energy exchange under security constraints between fast units in real time with zero energy balance. It provides a new way to enhance the value of flexible units connected to the electrical network and could lead to a better integration of renewables in the system. The basic idea is to run a power flow optimizing fast responding unit set points in real time according to given bits, and it enables both internal and cross-border trade. So that was the objective while this proposal was written, of course. So in that specific demo where we are now, so the ELES transmission system operator from Slovenia, where I'm working, is actually leading this work package. So we would like to achieve close to real-time activation of the renewable energy sources between Italy and Slovenia. So speaking about the hydropower plants, one from company Enel and one from company Hidrodolomiti Energia in the Italy side, and in the Slovenia, the hydropower plant from the HSE company from Slovenia. Involved are, of course, two transmission system operators. On the Italy side, Terna, and on the Slovenia side, ELES. Actually, I will show you a few insights and experience gained through the integration of the Flex Energy Market platform integrated in the real IT environment of the ELES business IT environment. And of course, the objective is, as it was said before, so the new products development and the market transformation. As you can see on this slide, this is quite a lot of information, but nevertheless, just I want you to get the feeling about the complexity of the demonstration test design. So while I am explaining you this, have in mind that actually we are doing the real pilot in the real environment. So it is not the simulation environment or lab environment, but we are speaking about the real stuff integrated in the production environments of the energy system, electricity energy system. So on the right, you can see my cursor. They are the generation cross-border exchange between Slovenia and Italy, as I mentioned before. And these blue lines you can see here are actually SFTP data flow connections. So between energy providers. On upper side you see HSE, so Slovenia, and down HDE and Enel. On the left side you can see so the two TSOs which integrated blocks of different functions. Upper is so ELES, wherein this Flex Energy Management platform consisted of three different software tools is integrated, and in downside you can see the Terna, so Italian TSO block, which shows the exchange the output activation signal for Italian side of the power plants, which goes to another data transfer signal on the ICCP protocol. Here you can see actually the high-level architecture of flex energy management platform. So on the upper left corner with the pink, you can see actually the three software tools which are gathering the information. So we are gathering close to real-time snapshots from the state estimators from the France, Northern Italy, and the Slovenia. So in order to have to achieve the observability close to real time regarding the power flows, this is needed, of course, for the calculation of the security constraints, while we would like to activate those generator units I mentioned before. And on the other side, the optimization tool, which is made by RTE from France, which also is taking account these economic constraints of the bits, because all of the participating units before the process you will see in the slide after, of course, they send the candidate bits in order to be executed in the future. So actually, this is quite innovative way, speaking about integrating such of complex software into the real IT environment of the transmission system operator. So all this data is then, of course, gathered and calculated, and the output of this flex energy management platform is actually so-called flex energy bit, which then goes into the SFTP ELES output server, which you can see here with my cursor. And then this activation signal actually goes via SFTP protocol into the ELES TSO SCADA production environment, where actually it goes then wherein this is transformed into the ICCP signal, activation signal, which goes then from the ELES ICCP channel to Slovenian HSC provider of the generation, and to the other side it goes into the SCADA system of Terna, which then is sent from SCADA system Terna into the NL and HDE activation units. And then, of course, the activation happens. And then, of course, it is created the back loop of the information while the activation happened, of course, for the settlement and notification of the executed bits. So we get then the closed loop of this process. Here is just for the illustration the time horizon. So we are speaking while we say near to real time. Actually, all this happens in approximately 15 minutes. So at the time when the snapshots from the state estimators are collected till the real activation happens. So a lot of processing is happening behind, and it's a quiet success that we are actually now getting the first results of the open loop and closed loop test of flex energy management platform right now. So we are expecting to start the closed loop test of all this whole mechanism I've described to you in brief actually in the summer. So we are expecting the first holistic results of demonstration test on September. And then, of course, we will be pleased to share the experience with wider audience about the flex energy market design and demonstration test results. So key takeaway, what I would like to message you regarding this experience coordinating this integration of the software tools and creating this flex energy management platform and the IT challenges of the connecting those blocks you've seen in the slides before is that we tackled on the few issues or challenges. So definitely first is the cybersecurity. You know that the TSOs are actually operating the critical national infrastructure. So it was and it is a quite challenge. So how to secure all these data transfer. And of course, there are also VPN access of the partners, which must be enabled. And we manage them successfully, and we are quite proud of it. Also, we would like to at least recommend that, of course, for the optimization of the speed of all these complex processes you have seen from gathering the data to the activation, we would like to upgrade these SFTP protocols into EcoSP into a platform in order to optimize these parallel processes which are happening in these 15 minutes. Definitely the observability close to real time, we see that it is important to move into the ENSO-A interconnection into the VAMS systems. So we will definitely encourage the TSO community and Acer also as regulator to speed up the processes regarding these VAMS technologies in order to have the common grid model. And of course, the last one, but not the least, these optimization methods, of course, must be also researched and optimized, and of course, then to find the optimal one. And thank you all for listening. That would be all from my part.
Thank you very much, Gregor. So far, we have no question in the Q&A section. Maybe I leave 1 minute if anybody has a question. Otherwise, we'll move to the next presentation. And you still have time afterwards, after the whole presentation for questions. All right, so no questions so far. So yes, one is popping. Take it. Okay, so one question for you, Gregor, before going to the next presentation. Do you consider delay loss of packages? How is it considered and which actions are taken to deal with them?
Sorry, can you repeat, Nathalie?
Yes, do you consider delay or loss of packages? How it is considered and which actions are taken to deal with them?
Okay. So the whole mechanism is actually ongoing. So it is while it will be the tests will be performing. So it will be like the principle that there is no need, you know, that these activations are actually happening, you know, continuously. So if the the algorithms will actually have these constraints that if something is missing, this set of the activation simply won't happen, you know. So yeah, but so far I can say now, but it would be a lot of easier to answer this question while actually this whole mechanism will be in the closed loop testing, like I said, in the summer, and maybe then we will manage to perform some additional adjustments, and maybe with some minor changes it will be possible also to work with some lacking information. But for now, for sure, as I can say that the whole so the whole inputs must be fulfilled towards the activation that happens. So the straight answer is if something will missing in the set, the activation won't happen.
Okay, great. Thank you. Great. Thank you for your answer, Gregor. So if you have other questions, you can put them in the chat. And now we'll move on to the presentation of Mandevi Rainevo from ACA and representing the EU-SysFlex project. And so we'll present us a demo which is more focused on let's say a generic platform for data exchange, and so is more general than the one presented by Gregor, but offer a good complementarity. Please, Mandevi, the floor is yours.
Thank you very much. Good morning, everyone. So my name is Mandevi Rainevo. I'm working for ACA, and in the EU-SysFlex project, we are playing the role of an IT provider and integrator. And as such, we are part of the team that has specified and developed the flexibility platform demo, which I will be presenting today. So this presentation will be given from the perspective of an IT provider. So first, what kind of flexibility platform we have implemented in this demo? So it is based on the single marketplace approach, in which we have on one side the flexibility buyers, and on another side the flexibility providers, and they trade flexibility products. As you can see in the figure below, you can see the flexibility platform in the bottom left, and you can see the flexibility buyers, let's say, represented here by the transmission system operator and distribution system operator, and on another side you have the flexibility service providers, represented by the aggregators, and using the affordable tool that I will talk about later. So one important point here is that with this approach, we have the same resource that is shared potentially by multiple flexibility buyers, and at the same time. Another important point is that this single marketplace offers opportunities to the, let's say, the small flexibility providers to access also the market more easily. And another role of the flexibility platform is that it allows de facto in coordination between the transmission system operator and distribution system operator, thanks to common flexibility products, thanks to coordinated grid impact assessment, all of that supported by the use of this flexibility platform. So regarding the demo, in this demo, we have demonstrated some flexibility market processes. Those processes have been described first within the system use cases developed by other tasks in EU-SysFlex. Those processes are about pre-qualification, the bidding, the activation of the flexibilities, and also the verification of the activated flexibilities. Very important to note is that we focused on the data exchange that support the processes cited earlier. And in that aspect, we have considered two main aspects. The first one is about the data model that is used for data exchange, the description of the business objects that represent the information exchange between the different stakeholders and the systems participating in all the flexibility market processes. And the second point is the use of a data exchange platform. This is an approach that will be, I think, described also later in a future presentation of this webinar. And the usage of this approach of a data exchange platform allows interoperability and scalability, as we will see later. So here we have the high-level architecture of the demo. As you can see, we have the flexibility platform in red, which is a software application with some user interface for the operator to interact with also all the solution to support the logic behind the processes, and also the persistence feature to support those as well, the data model that we have described. On the left, you have the system operator simulator. In fact, it is a simulator of system operators IT system, which is responsible for let's say the technical data exchange between with the flexibility platform. And on the right, we have the affordable tool, which is a software tool that is developed in another EU-SysFlex demo that allows small flexibility providers to access the energy market thanks to an aggregator operating this tool. And as you can see, in the middle of all of those systems, you have STFeed. STFeed here plays the role of the data exchange platform. It is a data exchange platform that is operated by ELES and with some technology from Cybernetica from Estonia. And it is responsible, as you can see, of let's say to support the data exchange between all the systems, and to ensure interoperability, but also scalability in form of cross-border exchange, because the flexibility platform and the system operator simulator were developed by ACA, so in France, located in France. The affordable tool was developed by Enoco, located in Norway, and the STFeed part are from Estonia. So here we have a cross-border exchange between all the systems. Here I'm showing the IT solutions that we used in the development of the flexibility platform and the system operator simulator. It is based on a three-tier architecture. This is a classical IT architecture where you have the presentation layer, the user interface, the backend, which is where the processes are implemented, and the database in which we have the persistence features. And we had to rely on a tool for time scheduling as well, which is Celery. Those tools have been chosen to support fast and agile development, because during the development of this demo, the specification were also described and updated in parallel. So we have to be agile and react quickly to the updates of the specifications. I was talking about SFeed, which is a data exchange platform. One important feature offered by SFeed is regarding the security mechanism. As we have seen in the previous presentation, it is a very important feature to consider. So thanks to SFeed, the security mechanism regarding the data exchange, data encryption, authentication, or let's say relieved from the developer of the systems, so that they can concentrate on the development. But then for regarding the security of the real data exchange, it is under the responsibility of the data exchange platform. And also this data exchange platform offers interoperability through uniform interface. Here we have used REST APIs for the exchange of requests and responses between the systems. So as I said, we have chosen the previous two IT tools for fast and agile development. But also, if you consider a very large amount of data in terms of big data, and you want high performance regarding that, we have also developed this big data architecture framework that can support batch and real-time processing of very large amount of data, and also on which we can run AI algorithms. So I will not go into the details of each of the components, but this can be used and can be considered when we are on searching, for high performance regarding a very large amount of data. And it was tested and compatible with the data exchange platform SFeed. So results and conclusion. So in this demo, we have demonstrated the data exchange between different stakeholders participating in a flexibility market. So in the heart of this demo was the flexibility platform, supporting the processes and the coordination between the different stakeholders. Among the stakeholders, we have the system operator, using the system operator simulator in our case, and the flexibility service providers represented by the aggregator using the affordable tool as described earlier. The key aspects for the data exchange, as we considered in this demo, was first the data model, in which we have described the business objects and the information exchanged between the stakeholders. It ensured interoperability as well between those stakeholders. And in fact, we had some work in order to go even further in terms of interoperability, sorry, and in order to map this data model with the common information model in order to have a even more standardized data model. Second key aspect is the data exchange platform, which ensured the interoperability between the participants of the data exchange platform by offering uniformized interface. Scalability, we have seen that we have some cross-border data exchange, and also very important security mechanism to secure the data exchange between the systems. So here you can see all the partners that have participated in the specification and the development of this demo. So thank you very much. If you have any questions, I would be pleased to answer. Thank you.
Thank you very much, Mandebi. So one quick question before going to the next presentation. What were your biggest problems and how could you overcome those? I don't know if you can answer rapidly to such a question.
Biggest problem. There are always lots of problems when you deal with, let's say, digitalization. But here, since we come from the IT perspective, we had to, let's say, understand what the domain specific aspects by discussing with the domain experts. And it was really interesting. It was quite a challenge, but it was really interesting. And we have to have the same understanding to develop together this kind of solution. This is a very general answer, but I hope it answers the question.
Thank you very much, Mandebi. We'll move to the next presentation now. So from Professor Mario Paolon. Yes, you have the control. So Professor Mario Paolon will talk about a different topic, more related to the new service which is arising and which is grid farming, and what the challenges relating to its performance assessment. So Mario, the floor is yours.
Thank you, Nathalie, for the very kind introduction, and good morning to everybody. So as Nathalie already said, the presentation that I'm going to give you is specifically related to a technical aspect, which is the quantification of the relative benefits of using grid forming versus grid following controls of battery energy storage systems for controlling the frequency in power systems. That, as you may know, is one of the key problems in the integration of stochastic renewables, since they may have issues in providing primary frequency containment reserve. Now, the objective, as I said, is to make this assessment by measuring the impact of grid forming units on the local grid frequency. Now, why I'm specifically saying this? Well, simply because the experimental activities that we are carrying out are making use of megawatt class devices. So estimating the impact on the system frequency is very difficult because actually they are too small to influence the frequency of the European power grid. So we had to develop methodologies and metrics that were capable to assess the impact on the local frequency of the grid, and I will come to that point in a moment. So the activities were both referred to a demonstration using a utilities scale battery energy storage system that we had on campus. I will give you the details in a moment. And then what we did is to also assess the impact of grid forming control units using real-time simulations on systems of relatively big scale, like the IEEE 39 bus benchmark. And then what we wanted to do is to compare whether the metrics that we obtained and we determined in the experimental demonstrator were similar to those that we obtained into the real-time simulation, and whether they were matching, and this was the case indeed. Now, few concepts to recall. What is a grid forming unit? Well, essentially is a power converter where the control is variable, is the magnitude and the angle of the voltage at the point of common coupling, which is essentially the point where the converter is interfacing with the grid. So this control does not require the knowledge of the fundamental frequency phasor of the grid, since this can be reconstructed and using a PLL-free controller. Of course, with this controller, you have also outer control loops that are essentially responsible of providing the set points of the droop values for active and reactive power to provide primary frequency controls or primary voltage control. Instead, in a grid following unit, what you are controlling is the injected currents with respect to a reference, and this reference is typically given by the voltage phasors at the point of common coupling. So therefore, for these controllers, you do need the knowledge of the fundamental frequency of the voltage phasor on the grid side. Typically, this is done by a PLL, but there might be also other techniques. And then to provide primary frequency and or voltage controls, you have typically outer controllers that you have here that are implementing the droop. But as you may know, these controllers are outside the control of the injected currents. So they physically behave in a very different way with respect to a grid forming unit. Now, these are pretty standard concepts. What we did in addition to that is to couple these grid forming and or grid following controllers with an optimal controller that is also taking into account the dynamics of the DC link, in this case, the dynamics of the battery, and the fact that your power converter cannot provide the amount of power that you can always request, because there is a capability curve that you see here in this figure, which is essentially determining in the PQ plane the region of space where there are the feasible operating points. Now, the problem is that this capability curve is not constant, but actually is compressing and enlarging as a function of the DC and the AC voltage. So what you should do when you're coupling your grid forming or grid following controller with your optimal controller, you have to take into account the dynamics of the AC and DC links. So what we did, and these are the results of a recently published paper on the interoperability transactional smart grids, is to propose and formally prove two theorems that are taking into account these dynamics of the AC and DC links, in particular the dynamics of the DC links. And before issuing a control action on both controllers, we are able to be sure that these control set points are feasible from the capability point of view, taking into account the voltage dynamics. And for us, this was a pretty interesting result. Since this optimization framework is convex, therefore it guarantees uniqueness of the solution and can be solved in practically real time. So we show in the paper that we can solve these problems in tens of milliseconds. That for providing primary control services is fundamental. Now, which are the metrics that we used? We used mainly two metrics. The first one is relative ROCOF. The ROCOF is the rate of change of frequency, which is essentially the derivative of the frequency. But what we did was to normalize the ROCOF with respect to the delivered active power to provide a primary frequency control. Why we did that? Because essentially we wanted to make the ROCOF, relative ROCOF, independent from the actual frequency variation. Otherwise, we could not measure the impact of the controller performance on the grid. That's why we had to normalize it. And then the second metric is the integrated phase angle difference deviation. Call it also iPad, which is not an Apple device, but it's a metric. And essentially, this metric is quantifying the deviation of the phase to neutral voltage difference between 2 points of the grid, typically measured by phasor measurement units, again normalized by the power that is provided by the converter. And the difference on the numerator of this formula is with respect to delta zeta 0, where delta zeta 0 is the angle phasor difference if there would have been not any injection of power from the controller. So essentially what you want to quantify is how much your phasor angles are opened with respect to the case where there is no converter that is providing these primary control actions. Now, a few words about the demonstrator. So the battery we are using, it has a nominal capacity of 720 kVA, well, close to a megawatt in overloading conditions. Energy-wise is 560 kilowatt hours. We are connecting the system to the 20 kilovolts grid of the EPFL campus. DC bus voltage is between 600 and 800 volts. The cell technology is a lithium titanate oxide for the negative electrode. For the positive electrode is a nickel and is an NCA technology. We have 9 racks in parallel, 15 modules in series. So the cell configurations per module is 20 S3P. I mean, there are more than 8,000 cells. And here you have all the specifications of the system. And here you have also a couple of pictures of the container, which is housing batteries, converter, and the step-up transformer to connect the system to the 20 kilovolts network of the EPFL campus. Now, I don't know why it's not advancing. Okay. In terms of measurement, phasor measurement units, these are devices that have been historically developed by my laboratory. They are embedding what we call enhanced interpolated DFT to estimate the phasors of voltages and currents. These PMUs are characterized by total vector errors, which are in the range of 0.0x%, which means that they're extremely accurate. Just to give an idea, they have a standard deviation for the phase estimates, which is in the range of tens of microradians. And these conditions are, these performance are guaranteed also in the presence of high harmonic distortion levels and high dynamics. Frequency errors were in the range of 0.4 millihertz. Reporting rate is 50 frames per second, very standard for the PMUs. And here you have also other characteristics. In terms of instruments transformers, we are using devices from Altea, composed by 0.2 class for the current measurements and 0.5 class for the voltages. This is the schematics of the grid of the EPFL campus. So the EPFL campus, as I said, is at 20 kilovolts. Actually, the rated voltage is 21 kilovolts. So this is the location where the battery container is located. And these are the 2 PMUs that we are using to make to estimate the metrics I was introducing before. So essentially, we put the PMUs on the high voltage and the low voltage side of the step-up transformer of the battery, because in the middle I have an important impedance, which is the one of the transformer, to estimate properly these metrics. And then the whole system is connected to a 50 kilovolt system, which is the sub-transmission grid of Lausanne. At the moment, we are also installing a PMU on the 50 kilovolt system to redo the study by adding more impedances in the middle and have a better estimation of the various metrics I was saying before. So here I also have the characteristics of the transformers in terms of power and short circuit values. In terms of IT architecture, where essentially there are 3 main blocks. There is the BSS container, which is the battery container, where we have a local secured network where we can communicate to the strings and to the converter via Modbus and EtherCAT. And this communication is done by a BSS controller. This BSS controller is also connected to the database, which is accumulating data from the PMUs. So the PMUs are streaming data through the IEEE protocol C37118. And the retrieval of the data is also happening in real time. And just to give you an idea, the latency here is about normally tens of milliseconds. And then outside, we have a server, which is storing all the data that are collected by the PMUs and by the BSS. This is how the architecture has been designed. Regarding experimental data, I'm showing you some of them. We have a bunch of data that have been collected so far. So this is a 20-minute test that was carried out a few months ago. Well, actually, yeah, on September 9, 2020. You know that when there is a rollover of the hour, very frequently in the European network, there is a drop or an increase of the frequency. This is an effect which is very well known, and it is due to the market imbalances that are accumulated at the end of the hour. So this was the case indeed. So the frequency was experiencing a change of about 100 millihertz. And here you can see the injected power of the battery. And here the battery was controlled as a grid forming. And here you can see on the right, the angle difference between the 2 PMUs during this control action of the grid forming of the battery. The same test was performed on the same day, 2 hours before, using a very similar drop in the frequency, using a grid following control. Just to note that the droop values that we use in grid forming are exactly the same, so 1.44 megawatts per hertz. And here again, you can see the SS active power and the difference of the angles of the PMUs. Now, if you look, we compute the metrics for these 2 experiments. In particular, here I'm showing the relative Rokov. you see the cumulative distribution function for the grid following in blue and the grid forming control in red. What you can notice is that the CDF of the grid forming of the relative ROCOF for the grid forming control is way steeper. What does it mean? Well, it means that the capability of the grid forming of let's say, having a lower relative ROCOF is way better than the grid following. So essentially, the impact on the local grid is to decrease the amplitude of the ROCOF, which is eventually what we wanted to achieve with grid conforming control units. If you look at the iPad, what you want to do is exactly the opposite. So you want that your grid forming control is injecting power such that it's opening up the phasor angles as much as possible. And again, you can see here the CDF of the iPad for the grid following and grid forming control. And again, you see that the metric is in favor of the grid forming control unit, showing its superiority with respect to the grid following. Again, these are data collected by these two PMUs that you see here, highlighted on the experimental facility we have on campus. And again, are metrics on the impact on the local system frequency. Now, what we wanted to do is to say, okay, now we have very good results that are experimental ones, but what if we scale all this to the level of a transmission system, okay? So as you may know, typically in research domain that is specifically working on this subject, we use real-time simulators. So what we did was to take the IEEE 39 bus system, manipulate it in order to reduce the amount of generation from synchronous machines and replace it by using wind turbines to reduce the inertia of the system. And then what we did was to run a day-long simulation, where essentially we have a day-ahead schedule for the demand and wind generation forecast. We compute using NSOE rules of frequency containment and restoration of resource allocations using exactly what is done in Europe nowadays. We do a unit commitment to provide energy generation reserves schedules for the next 24 hours, and then we run it. And we run it to compare the performance of grid forming versus grid following controls using a battery energy storage system. So this is the topology of the system. You can download it for free. It's an open source model on GitHub. This is the location of PMUs, very similar to what we did before for the real case, real measurements. And what you see here is that the integrated frequency deviation for grid forming and grid following for different values of the droop, again, is in favor of the grid forming control, showing again its superiority. The same thing happens if I took back the relative ROCOF. You see exactly the same behavior that we have obtained experimentally on the EPFL campus. Essentially, the grid following is capable to compress the relative ROCOF, even if you're running this experiment at the level of a relatively big system. I know I'm running out of time and I will jump to the conclusions. I see that Nathalie is already showing her image. I'm done, Nathalie. So just to conclude, the OSMOSE demonstrator EPFL is specifically designed with an architecture capable to assess the performance of grid forming versus grid following controls to estimate the impact on the local frequency. So the experiments have on the EPFL demonstrator has quantified the superiority of grid forming versus grid following controls in terms of frequency performance and frequency containment. We extended this study to the case of the IEEE 39 bus benchmark, and also via this simulation study, we confirmed the superiority of the grid forming control versus the grid following to compensate the fluctuations of the frequency. And as a conclusion, we do believe that this is a way to go in order to, let's say, limit the impact on the frequency dynamics of volatile renewables that are characterized by lack of inertia. This is it, and I thank you for your attention. Sorry if I was too long in my presentation.
I thank you very much, Mario. I think we have two interesting questions in the chat, but I suggest that maybe you can try to answer them directly in the chat, Mario, so that we can move to the next presentation.
Okay, no problem.
Thank you very much, Mario. So now we'll have Emeline Guillou from RT, which will present, let's say, the TSO view on the challenges to monitor new services. So, Emeline, the floor is yours.
Thank you, Nathalie. So my name is Emily. I'm working at the R&D department of RTE, and I'm going to talk to you about the new services which enable the system stability, and more particularly their monitoring. Next slide, please. So as Mario presented just before, grid forming is a function which can be performed by different ways. And the important point is the service provided. And so grid forming function should be specified without taking into account technological aspects. The principle is the same for monitoring methods, whose role is to discriminate grid forming from grid following behavior. The final objective is to make sure that system needs are fulfilled all the time. Next slide, please. So grid forming function is part of the set of levers used to maintain the equilibrium of the system. Indeed, new phenomena are going to appear with increase in renewable energies connected via power electronics. One of these phenomena is the decrease in inertia and consequently the increase of frequency deviations for the same event. It's the slide before. One slide is missing. Next one, please. Okay. Well, it doesn't matter. Go before, please. So one slide is missing, but it's nothing. So the frequency will vary more because of the decreasing of inertia, and so the minimum transient frequency will go lower, and to maintain the stability system, that is to avoid frequency load shedding. Some services will need to be adapted. For example, a faster time answer for frequency containment reserve, or other services will need to be created. For example, in Great Britain, and frequency response has been created, which is a faster frequency response, which gets along with classical primary control. And grid forming, which is a new service, would be able to react immediately, and so can be considered as fast as inertial response. So next slide, please. For each new services, once a new service will be identified, it will be necessary at least to know which technologies can provide it and which signals have to be monitored to be able to discriminate. If necessary, signals to be processed should be adapted. For example, we will need a shorter time scale data, or we need a better measurement resolution. To assess the efficiency of the regulation, specific monitoring methods, potentially local, will have to be implemented. Regarding IT aspects, the evolution of the services will impact the amount of data to deal with, because there will be much more installations to monitor in the future. It also impacts the equipment to be installed, because the minimum required quality of the data measurement will be more important. There will be also an impact to the control locations. For example, continuous locale monitoring will be done with only specific event reporting in order to limit data flow. Next slide, please. And the next steps consist in determining the minimal needs to ensure the system stability and security, not only globally, but potentially locally, as I said before. Once the needs well known, service provider requirements could be established, that is expected performances and also settable parameters. It will be then necessary to demonstrate the effectiveness of proposed monitoring methods in large-scale applications before adopting this in the network codes. Thank you for your attention.
Thank you very much, Emily. And so we'll move to the next presentation from Callie Cook from the EU-SysFlex project and from ELES. So we present us some conceptual model for private energy data management, which has been developed in the EU-SysFlex project. Kelly, the floor is yours. We cannot hear you so far. But...
Thank you. I guess you can hear me and see me as well. Yeah, it took some time to unmute me. So indeed, I am here to talk on behalf of EU-SysFlex again. And the approach we had in the project and still have until the end very soon is more on the conceptual level. So we had a dedicated work packages to develop some use cases for the data management as such, but especially focusing on the private data, because this is increasingly important for our sector. And based on these use cases to develop further some conceptual data models, assess the standards needs, etc. And then all these were demonstrated in a set of small scale demos. In fact, the one previously presented by Mandimbi was the I would say the largest one and the most interesting one on the flexibility platform. So there we demonstrated a set of those flexibility use cases. But if we move on to the next slide, so the topics to be discussed now is the general objectives for data management. We had then to tell you the story how we elaborated this conceptual model, then some evidence from the demonstrators, the Flex platform demo, but also the others, and finally some key messages. Next slide. So I would start with some keywords like customer focus and interoperability. So these are the two main keywords we have built our conceptual data exchange model around. And as such, we say that it is customer-centric, but also cross-border data exchange for flexible market design, serving several stakeholders. So it's a kind of multi approach. You see that we wanted to develop a framework which is not specific to, as much as possible, of course, but not so specific to any specific business process or specific actor in our field, etc. So our focus is to really develop something very agnostic that should work for cross-border approach as well, for cross-sector approach even, and would also support any stakeholder in our field. And as such, to start from customer-centric approach seemed to be quite useful. And to demonstrate here to you this well-known SCAM framework, we were mapping some elements to basically each interoperability layer of this SCAM framework. And here you see some elements we then have gone through in our work package on data management, starting from the assessment of the legal requirements and ending up to standardization, gap analysis, and many others. Next slide, please. So these are just some snapshots. What we have done and what we have also published already is on the right side, the paper on the role model. So based on the use cases, we identified many roles. We mapped them to the harmonized role model. So we took it as a kind of reference model, and I think it's always useful to have a kind of jointly agreed reference model where we all can map our findings against to, so indeed then all our projects, but also beyond the projects, the way of working and the results are really comparable. And in this data role model, we just also identified some new roles which we think are useful. And since our work was from the data perspective, these new roles also mainly were focused on the data roles. For example, the data exchange platform operator or authentication service provider. And on the left side, the next step, or one of the next steps, actually the one to finalize our work with, is to map all those use cases to the SCAM plane. Just an example here, but basically what we do, and we more or less have done already, also thanks to the colleagues from ACA again, we have taken all of our use cases, the system use cases, and mapped them to this SCAM plane, the zones, domains, and also the interoperability layers. Next slide, please. So here on the left side, then the use cases I've been mentioning. So the 16 or in fact 17 system use cases. And if you look at the list there, and this is also the deliverable available, and all the use cases are available on our website. There are some which I mentioned before as flexibility use cases maybe. So these were the ones basically demonstrated in this flexibility platform demo. For example, manage flexibility activations or calculate flexibility baseline. So these are use cases maybe less agnostic to specific business processes, as you can imagine. But still, we try to describe them in a way that they could work in different market designs as much as possible. But the other set here, you can see like anonymize energy data, or erase and rectify personal data, or transfer energy data. They are really general in that respect, that they are not linked to any specific business process. So they can work for any process, and even beyond our sector, the electricity sector, they can work everywhere. So what we had in mind to try to describe this use case in a way that it could also support cross-sector data exchange. And mostly, if you look at the list, and to repeat again, it's all about exchanging the private data, almost all. So it is increasingly important. And this is on the right side, one of our newest deliverable recently published on the security and data privacy. And this is just a small table from there to link the GDPR rights to our system use cases. Next slide. So another message I wanted to elaborate here a bit was what I see increasingly raising in the discussions is the solutions-based approaches and standards-based approaches, or you can put it also open source versus open standards. And the question mark really implies that for me, it is not, or at least it should not be actually versus. So they are not opposing each other. They rather should support each other. We looked at both in a way. So on the left side, this is another example from another deliverable on the big data, also available on our website, is where we again took the same 16 system use cases you see around this radar chart, and the colors here stand for 4 data platforms or kind of data sharing concepts, like the S-feed of ours, but also Green Button is another, and Norwegian Data Hub was the third one. So we made that kind of assessment that we took these 16 use cases, actually the specific requirements of those use cases, and then mapped them to those few selected data platforms. So to see how these platforms actually today support or do not support those use cases. And on the right side, it's the example from our standardization deliverable, also available now. So we also focused on the standards assessment. We have gone through a long list of existing standards, and try to understand and identify whether there are gaps in standards, again, related to those specific use cases. So again, we mapped the standards to those 16 use cases. And our primary focus was on SIM, and then we concluded that, for example, SIM extension would be needed for consent management. Next slide, please. So some demos, really seeing the clock ticking, I go through them. We were presented the flexibility platform demo, but all the demos, again, are around this data exchange platform concept. You see it on the left side, the S-feed globe, so to say, and all the stakeholders are around that globe and communicate with each other through these S-tweets. So it enables to set a single interface instead of many interfaces with many of the stakeholders. Next slide, please. And other two examples, the big data demo also was briefly mentioned by the Mandimbi, but also we had these other demos looking at the cross-sector and privacy elements. But I guess we need to scroll further now. The next slide is then to conclude some key messages, which I also mentioned. So the data role model with some new roles illustrates the increasing importance of data exchange. Interoperability at any SCAM layer through open standards and open source approach. So don't ignore the other. Then focus on data platforms, but as I said, the model should enable a mix of different data models. So it can be central, decentralized, distributed, and data governance model, either standards-based or open source. System use cases, I explained a lot, should be agnostic as much as possible. Simification was the process we came up with exactly to map the flexibility data exchanges and private data exchanges to the SIM data model. Data privacy for private data, quite clear. And finally, several demonstrators of ours proved the usability and approach based on data exchange platforms. I guess that's it from my side. Yes, indeed. Thank you.
Thank you very much, Kalle. If there are questions for Kalle, I suggest that you put it on the chat and Kalle can answer directly. Or maybe we'll take a few minutes after Camille's presentation to take some questions directly. So Camille Bloch from Schneider Electric will present us some key benefits from the IEC 61850 standard. So Camille, the floor is yours.
Thank you, Nathalie. So I am Camille Bloch, and I am coming from the OSMOSE Work Package 7.1, which deal with interoperability study on how we can take benefit of interoperability offered by standard in the overall OSMOSE project. Next slide, please. So first, we talk a lot about, during all of these presentations, we talk a lot about the need of interoperability and the need of data model. And in the last presentation, we focused also on the possibility to use SIM as standard for data modeling. And if we are looking at the smart grid architecture modeling, the SGAM, they already identified two main standards to address this. This is the first one, SIM, which is more focused on the market and the enterprise level, and IEC 61850 for the operation level. Yes, 61850 is more operational than SIM, but he offered the similar approach as SIM by offering three main aspects of 61850, making this more than a simple communication protocol as we often hear. So first aspect is the modeling, so to give a standardized semantic to the information exchange, exactly as the same as SIM, but for other purpose. Then the second one is standardized engineering to have the same workflow between the different actors of the system to be able to engineer the overall system independently of the different manufacturers or providers which will be integrated in the system. And the last one, which is, in my opinion, the consequence of the two previous, is the communication. So 61850 also come with a standardized way to exchange information, covering two different way of data exchanging: the event-based point-to-point communication, so the so-called client server, and the other one, which is the fast broadcast communication to ensure properly the protection functions. And so the goal of all of these standards aspects is to offer interoperability between all vendors participating to a project. Originally, 601FTT was designed for substation communication, but now these principles are defined independently of the domain. So it is for sure for substation, but now we have also extension of the standard to support DER data modeling, as such as wind power and hydro domains. Next slide, please. So now I will focus more on something which may interest the current projects, how 601FTT may benefit. So 601FTT proposed to replace all technologies. First, legacy protocols. You can see on the right the old way of doing systems with different kind of devices, protection IED, control IED, meters, which communicate between together with a lot of protocols, Modbus, DNP3, 101, 104, and so on. So this continues to have different implementations. So with a risk of loss of interoperability if some manufacturer has not implemented this in the right way. And at the process bus level, so the communication with the process, all manufacturers has come with their proprietary implementation, most of the time wiring communication. And IEC 601FTT proposed to have one standard to make the interoperability available between all devices and for the station bus, but also for the process bus. Now, process communication is standardized, allowing to use new kind of devices which are intelligent, like intelligent sensors and controllers, directly connected to the process elements like circuit breakers, switches, CTVT, and based on efficient and reliable protocols. So GOOS and sample value protocols are two new protocols introduced in 601FTT. To have a predictive and reliable exchange between the different devices to be sure that we are not tripping circuit breakers or switches too late. And then, now please come back to previous slide. And then also protection functions are supported by 601FTT protocol and with interoperability between vendors with the performance required to protect the system. And last point, which is a good benefit, is that 601FTT is a live standard continuously evolving to integrate new domain and function and new protocols. For example, we are working to integrate electrical vehicles, system management function, traveling wavefault, and as a new protocol, we have implemented recently the web services. So for HMI, it could be easier to connect to IEDs, for example. Next slide, please. And more precisely, how 601FTT could be used in your projects. So first, DER domain is already part of 601FTT, like what you can see on the right side. So in 601FTT, we have defined different functions, which are called logical nodes in the standard. And as you can see, we already have implemented the different logical nodes related to generators, to load, and to storage. Engineering and communication with DSO is also already supported by 601FTT, and 601FTT offer mapping with legacy protocol. So this allows to interconnect new system using 601FTT with old one by defining a proxy device with the same semantic, but the address coming from the legacy protocol. And last point, to make link with the previous presentation, there is a new standard, so the 62361-102, which describes the interface between 601FTT and SIM to exchange information between the two levels. Next slide, which will be the last one. If you want to have more information about CCO and FTT, because this is really a fast introduction, I can speak more than 1 week to present the different aspects of CCO and FTT. So OSMOSE Work Package 7.1 has already provided a webinar 1 month ago, so you have the link here. There is also the presentation of the goal of the Work Package 7.1 also available here. And for more information, you have also a YouTube video where there is an interview of Christophe Brunner with the leader of the CCO and FTT working group. Thank you.
Thank you very much, Camille. So we are running a little bit out of time, but I suggest that we can, all the speakers, we can stay, let's say 10 minutes more if there is some questions from the audience so that we can address some heading questions. You can directly enter your questions in the chat. Waiting for any question, I will ask one from my side, maybe for Gregor, because I think Gregor, you have explained that in your demo you somehow developed from scratch a flexibility platform, whereas we saw that on the EU-SysFlex project they have designed some kind of generic platform for data exchange. What did you think about it? Is it something that could have helped you in your project?
Well, it's hard to say now. Definitely, it's interesting, and of course, take it into account because I believe a lot of uncertainties will be clarified while we will start with these demo tests and write those 2 last deliverables in which we will, of course, evaluate all these use cases and KPIs and actually test all these building blocks of closed loop tests in real environment. And I think after that, it will be the right time to contemplate and consider in which direction and under what directions we shall then recommend future steps even after this OSMOSE project will finish. So it is a little bit premature now to have the straight answer to question of yours. But definitely such platforms are, of course, interesting, and I think this is the way the things in the energy sector regarding interoperability and merging this triangle, we say, TSO, DSO, and aggregator should emerge in future.
Okay, thank you for your answer, Gregor. We have one question from Calais. You briefly showed in a slide about information data exchange architecture. And so where could we... Yes, okay, Adam, you can answer the question. The question, where could we find this in the project deliverables?
It's Kalle here. Yeah. So you probably, Petri, you mean this data exchange platform concept, or maybe you mean all of it. What I can say that there is one final deliverable still to come by end of this year, but there are many other deliverables also already available in EU-SysFlex website. So maybe I don't know if we can put links here in the Q&A on the system use cases. There is a good deliverable already available, and a few others. but the one what we call conceptual data exchange model, this will be out there by the end of the year. Thank you.
Okay, thank you. So maybe Adam or Christina, you can show indeed the contact details of our speakers in the last slide. Okay, great. So if you have any pending questions, you can send them to our speakers. And of course, you can also go to our website, so the OSMOSE and EU-SysFlex website, to search for more information. And our projects are not finished yet, so please, you can continue to follow up on our results and deliverables coming. And so I thank all the speakers for their participation and very interesting presentation, and very clear also, although sometimes very technical, but still with a clear presentation. Thank you very much to all of you, and have a nice day, and you can follow our next webinar tomorrow.
Thank you, Nathalie.
Thank you very much.
Thank you very much.
Thank you, Nathalie. Bye.
Thank you. Bye-bye.
Bye.